Welcome back, everyone. So this is the Introduction to Statistics and Psychology, and my name's Rob, and today's lecture is the second part of a three-part series on how to conduct one-sample t-tests. In the first part, we had gone over a refresher one-sample z-test problem, and in this part, we're going to compare and contrast one-sample z-tests with one-sample t-tests. In addition, we'll talk about the importance of using effect size, how to compute effect size. And then in the next lecture, in the third part, we will be looking at how to conduct a t-test in a more real-world scenario, whenever you're not given means and standard deviations and you're just dealing with raw data. So, as always, over here are the PowerPoint slides. And then up here is our virtual whiteboard. And if you find this video helpful, don't forget to hit that like button and click subscribe so you can get notifications for newer videos like this one. And please don't hesitate to leave comments in the comment section below. So on that note, why don't we get started with our explanation of why one would conduct a one-sample t-test. So what's the purpose of the one-sample t-test? Well, it's used to distinguish whether or not a particular sample is significantly different from a particular population. Another way to say this is, does the sample statistic that we have, does it belong to the overall population, or is it unique from the overall population? And so whenever we typically encounter one of these tests, we'll be given a population mean, and we'll be given a sample mean, and we'll be given a sample standard deviation. Now, the primary distinction between a one-sample z-test and a one-sample t-test is that with the z-test, we're given the population mean and the population standard deviation. However, there aren't very many times in the real world where we encounter a situation where we have the population mean and the population standard deviation. And so we still want to ask our question, but we're in a position where we'll have to estimate the population standard deviation using the sample standard deviation. And whenever we estimate the sample standard deviation, because we don't have the population mean, we're conducting a one-sample t-test. So a t-statistic is an alternative to the z-statistic. It basically takes into an account error based on the size of our sample, and it shapes the distribution such that as our sample size increases, our t-distribution approximates a z-distribution or a normal distribution. And so t is an approximate of z. And so we're going to calculate an estimated standard error, which is notated with S sub x bar, instead of using the real standard error, which is what we were using in the z-test, which is sigma x bar. So let's just look at the equations. And you can see, the numerator of both z and t is the difference between our sample mean and the population mean. And then the denominator, this is our error term in essence. Really, there's absolutely nothing different at all going on mathematically, right? So a z-test uses the population standard deviation divided by the square root of n, and a t-test uses the sample standard deviation divided by the square root of n. Now, another distinction is we have to look up critical values just like with z-tests, but instead of using the area under the normal curve table, the z-table, we use a new table called the t-table. And it provides you with the area under the t-distribution, and will give you a critical value for t, just in the same way as a z-test would. However, the distinction is that the size of your sample in the t-distribution determines The critical values change based on the size of your sample. So here's an example of this, right? You can see that whenever the t-distribution has a degrees of freedom of 5, it's farther away from its approximation of the normal distribution. But as the degrees of freedom, or sample size, increases, it becomes closer and closer to a z-distribution. And so, in other words, as the degrees of freedom for a t-distribution approaches infinity, it more closely approximates the normal distribution. So how do we conduct a one-sample t-test? Well, I mean, there's really not much that's different in terms of the procedure. We're going to set up our hypotheses. We're going to determine what the critical value is for us to reject our null hypothesis. And to do that, we'll use the new t-distribution table. And then we're going to set up a decision rule for the hypothesis test, compute the obtained value of t, and then determine whether or not we reject or fail to reject the null hypothesis based on the decision rule we outlined. And then finally, we'll write it up in APA style. So there's very, very little difference between a one-sample t-test and a one-sample z-test. The key here is we're taking away one crucial element of information that we had in the z-test before. In a t-test, we no longer have the population standard deviation, and we have to estimate it. And this is why we conduct the t-test. So let's look at an example, right? So we're going to do an example about an intervention to help children utter their first words at a younger age. So let's look at this example. So you developed a new technique in hopes of helping children start reading earlier. The average age of first word utterances in your town is 13 months, but you don't know the population standard deviation. You apply your technique to a random sample of 15 children, and the sample mean age of first word utterances is 11 months, with a standard deviation of 3.34. You want to test if your hypothesis is correct. In other words, if there are changes in the time of first word utterance. So to start off, we need to determine what test that we're going to conduct. And in this situation, we have a population mean, a sample mean, and a sample standard deviation. And we can use that sample standard deviation to estimate the population standard deviation. And so that's why we're going to do a t-test. So we are conducting a one sample t-test. And the next question we should be asking is whether or not this is going to be a directional or a non-directional test. And so the way we can determine this is look at the last sentence of the problem. You want to test your hypothesis if your technique changes the time of first word utterance. So the key here is we're looking to see if the technique changes the time of first word utterance. Doesn't increase in duration, decrease in duration. We're just looking for any change. So this is going to be a non-directional test. And like any good statistician worth their salt, you're going to draw the normal distribution. And since it's non-directional, we know that we're looking both above and below. And so now we need to write out our null and alternative hypotheses. And these are exactly the same as we did when we computed them for the z-test. So our null hypothesis is going to be that mu is equal to 13, right? So the null hypothesis says, nothing's going on. So we're saying that the population our sample represents is equivalent to 13, which is the the population in the problem. And for our alternative hypothesis, we're going to say that mu is not equal to 13, meaning that it can be different in some way. Okay, so the next thing we need to do is we need to find our critical value of t. And to do this, we're going to use our student's t-distribution table. Okay, and so I'll pull it up here on the whiteboard as well. And over here on the left-hand column, this is your degrees of freedom. Now, in a one-sample t-test, degrees of freedom is n minus 1. So we look down here, we had an n of 15. So we're looking at degrees of freedom for 14. And we go over and we're looking at 0.025 because alpha is set at 0.05. And we can see that our critical value for t is plus or minus 2.145. So, it could be minus 2.145, or it could be plus 2.145. And again, this is our rejection region here in the tails. And each one of these is half of the overall alpha. Since alpha is 0.05, each tail has 0.025 in the rejection region. So with this, we need to write our decision rule. And so the decision rule is basically a firm statement that says what we are going to do, how we're going to make our decision about whether to reject or fail to reject the null hypothesis. And so we're going to say reject the null when t obtained is greater than or equal to 2.145 or less than or equal to minus 2.145. And you can see in either situation, if our t obtained value falls within the region of rejection up here, we are going to reject the null hypothesis and say that our reading intervention was effective. Okay, so now after this, we need to compute our obtained value of t. So how do we do that? Well, here's our formula, right? And we have t obtained is equal to the x bar minus mu over the sample standard deviation divided by the square root of n. So we just plug in the numbers. T obtained is equal to 11 minus 13 over 3.34 divided by the square root of 15. And we can pull up a calculator and we can just solve for the denominator. 3.34, divided by the square root of 15 is equal to 0.8623. Okay. And so this resolves down to negative 2.319. So this is our t obtained figure. And at this point, we go back and we determine whether or not we should reject or fail to reject the null hypothesis based on the decision rule. So our decision rule states that we will reject the null when t obtained is greater than 2.145, it's not, or less than 2.145. And so it is less than 2.145. So our t obtained is falling somewhere right around here, and we reject the null. Okay, so what does this mean when we reject the null? Well, we reject the null and provisionally favor the alternative hypothesis, which is that our sample is different from our population, right? So it means that there's something going on with these children who received this training that makes them different from the overall population of children. Now, there's two things that could be going on that make them different. The first thing is sampling error. It could be that just by sheer chance, at random, we selected all of the really early speakers, the children who spoke at a really young age, just by sheer chance. And that would happen 5% of the time. And that's what our alpha means. However, the other thing it could be is that something's different about these children. And that's 95% of the time what it's going to be. So 95% of the time, our children don't belong to this population because of some other reason. And that reason is that they had the reading intervention, right? So what we're doing here is we're saying that there's a 95% chance that the reason this sample does not belong to this population is because of our intervention. So now we need to write this up in APA style. So, as with all write-ups, we do what did you do, what did you find, and what does it mean? And so here, what did you do? Say a one-sample t-test was conducted to determine whether a new reading technique for children would change the time children utter their first words. What did you find? Well, this is where we report our stats. We say compared to the general population of children and report the mean, those who received the new technique and report the mean and standard deviation uttered their first words significantly earlier. And then we report T parentheses the degrees of freedom that we used to obtain that critical value. And then our T obtained value. So it's very important not to confuse the T critical value with the T obtained value when writing this up. What you include is the T obtained value. And then after that, you report the standard error of the mean, which is simply the denominator in our T equation. And then we say that P is less than 0.05. And you can think of P as the probability that this result is due to sampling error. And so what we're saying here is that the probability that we would get a mean in these children so different from the population due to sampling error alone is less than 5% of the time. And then for the last part, what does it mean? The point of this is to just explain it very simply, clearly, so that a general population who aren't trained in statistics can understand what it means, right? And so we say this suggests that the newly developed technique was effective in helping children to begin speaking at an earlier age. Okay, so I hope that was a very helpful example. Let's continue. Let's ask, what would happen if we only tested 10 children in our sample instead of 15? Well, so we would need to look, here's the problem. All we've changed is that there's only 10 children in our sample, right? And so the idea here is that by reducing the number of children that we're sampling, we're actually reducing our statistical power. And we're introducing more error in the denominator of the t equation. So let's look at how that would pan out. So we would need to look up our critical value of t again. And here we can see that when our degrees of freedom is 9 for a non-directional test, we would have a critical value of 2.262. And then when we compute our t-test, so the hypotheses aren't going to change. The decision rule, we just swap out the new critical value, so we'll reject the null when t obtained is greater than or equal to 2.262 or less than 2.262. And then for our t obtained value, it's still the same in the numerator, but in the denominator, we have 3.34, same as before, divided by the square root of 10. And so this is going to give us minus 2 over 1.0562, which gives us a t of 1.8935. So now let's look at our decision rule. So we're going to reject the null when t obtained is greater than 2.262 or less than negative 2.262. But our t obtained only reached 1.89. So we fail to reject in this situation. But what does that mean? Well, we write it up, and here everything's the same with what did you do, but here we have, and the same means and standard deviations in what did you find. But when we report our statistics, now we have a t of 9 and a much smaller t obtained value and a much bigger standard error of the mean value. And now we say that p is greater than 0.05. And the reason it's greater is because the probability that we would get a mean this difference due to sampling error is greater than 5%, which means it's less likely for this to be due to our treatment, because over 5% of the time, it could just randomly, we could select children that read at that early phase. So then we write it up and we say that there's not sufficient evidence to suggest that the technique was effective. Well, that doesn't seem to make sense. Which one's correct? We did this problem with 15 students, and then we do it again with 10, and we get completely different conclusions. Well, so this is why we need to report effect size. So effect size is an index of the magnitude of an effect, and it doesn't take sample size into account. So oftentimes we can have in statistics a very small difference between two means, and it can be significant because we have a huge sample. On the flip side, we could have a really, really big effect that is not significant because we had a small sample. And that is what we just demonstrated. When we had 15 children, it was significant. We were able to reject the null hypothesis. But when we reduced that sample size and with it our statistical power, we did not have sufficient evidence to reject the null hypothesis and say that our sample was statistically different from the population. So just to inform your audience about what the magnitude of a particular effect is, irrespective of their sample size, we report effect size. So a common effect size index is called Cohen's d, and it's essentially the mean difference divided by the sample standard deviation. You can think of it kind of like a z-score, where it shows the magnitude of that difference in units of standard deviation. So the specific equation is quite simple: x bar minus mu over the sample standard deviation. And then once you compute it, we'll compute it for this problem right now. So we've got 11 minus 13 over 3.34. And so that's minus 2 over 3.34, which is equal to approximately minus 0.60. So once we have our effect size calculated, we can come here and interpret how big this effect really is. And here we can see 0.6 falls in the medium effect size range. So we would want to state that this is a medium-sized effect. So now we need to incorporate how to compute or how to report this effect size within our APA style write-up. So what did you do? Same exact thing. What did you find? Here's where we put it. After our p-value, we put d equals minus 0.60, comma, and then explain what the magnitude of the effect was. This is a medium effect. And so here, we have a medium effect. However, we have very, very low sample size. So it was not sufficient evidence for us to reject our null hypothesis. Under this information, we still don't know if the treatment works. So I hope this is helpful. If you have any questions, again, please leave them in the comments below or shoot me an email. And if you found this helpful, please subscribe and like the video. And I look forward to seeing you for the third part, where we will review how to conduct a one-sample t-test using raw data. Okay. Well, thank you very much for your attention, and stay safe, stay healthy.